In this video, we'll discuss post hoc comparisons, which are a series of comparison methods that can be used after a statistically significant ANOVA to determine where the differences in the group means are. So post hoc ANOVA comparisons compare the means of the different groups. Again, the analysis of variance tests all of the treatment means to be equal to one another, or all of the means within that factor to be equal to one another, each of the factor level means. Now, for this, we're going to just kind of assume that the assumptions are okay, that analyzing the residuals, nothing stood out. And again, the problem with ANOVA is that if the null hypothesis is rejected, we don't know where the differences are. We don't know if like one mean is different or maybe a group of means is different. So we want to be able to investigate that. And there's a couple of different ways that we can do that. So among other things, we could use just pairwise t-tests. We could do a t-test comparing two means and then look at another pair of means, compare the first factor level to the second one, compare the first factor level to the third one, and just do these pairwise, meaning picking a whole bunch of different pairs of factor levels, comparisons where we do these tests comparing these different levels of the factor. Actually, there's a formal name for just doing a bunch of regular old t-tests. It's called the Fisher's LSD method, the least significant difference. But there's a lot of other ways to do this. Now, the pairwise t-test is one pairwise method. So there's many pairwise methods. Fisher's LSD is one of them. And actually, in this class, we're going to focus on the pairwise methods because those tend to be a lot more common. Another one that actually is pretty common, and I wish we had time to go more in depth on this, is the contrasts. Now, that's in section 3.5 in your book. And what's cool about contrasts is they let you compare not just one mean to another, but they let you compare like a group of means. So let's say I wanted to compare the means of factor level 2, 3, and 5 as an aggregate to the mean of factor level 1 and 4 as an aggregate, and I wanted to do these kind of grouped comparisons. Contrasts allow you to do that, and if you design them orthogonally, it's something you can check out in section 3.5 if you're interested in looking at that. But in this course, we're going to focus primarily on the pairwise comparison method. Now we can determine which of the means differ after we run the ANOVA. So typically how this works is we run the ANOVA analysis. If it's statistically significant, that's when we do these comparisons. And these comparisons are called post hoc comparisons, which just means after the fact. So post hoc indicating that we run them after we ran the ANOVA. Now the problem is that when we start doing a whole bunch of different analyses, we run into what we call the multiple comparisons problem. So for the multiple comparisons problem, the main issue is that if we run a whole bunch of statistical analyses and we only have a 5% chance of being wrong on any one of them, then we expect at least one of them to be wrong. So let's actually look at this a little bit more in depth. Multiple comparisons and the family-wise error. So the family-wise error rate, this is a kind of a new term. So family-wise error, this represents the chance of getting a type 1 error in any test. So recall that when we set alpha equal to 0.05, we're comparing to 0.05. That is the rate of type 1 error that we find acceptable. The family-wise error is going to represent the chance of getting a type 1 error not in one particular test, but in all of the tests that we run as part of the experiment. So in any test we're running. So it's a slightly different thing. The problem with running a whole bunch of tests is that each one could have a type 1 error, and that's this multiple comparisons problem. So for example, if I'm running 4 tests, the probability of a type 1 error in any of them, with the type 1 error rate being 0.05, isn't going to be 0.05. In fact, we can calculate this mathematically. We plug in 0.05, we raise it to the power of the number of tests that we have, and we get approximately 0.19. So the family-wise error is about 0.19. What does that mean? That means if for every test we only allow a 5% type 1 error rate, nominal type 1 error rate, then the probability of getting a type 1 error in any of the tests, any or all, so at least one of the tests, is 19%, not 5%. And the probability of getting a type 1 error of 19% is way higher than what we're comfortable with. If we set the type 1 error rate, if we're only comfortable with a 5% probability of error, having a probability of error, type 1 error of 19% is immense. That's way higher than what we're comfortable with. And we have to account for this. And so there's a whole bunch of different ways that we can do. And that actually is what post hoc procedures are all about. The difference between post hoc procedures primarily is how they address this particular problem. How do they address the fact that we wanted an error rate of 5%, but because we ran 4 tests, we actually have an error rate of 19%. And again, there's a 19% chance for each test, but that is, if we have a 5% error rate for 4 tests, then the probability of a type 1 error in any of them taken as a whole is 19%. So how do we address that? That's the different multiple comparison problems that we're solving and the different post hoc solutions. So we've got several different approaches: Fisher's LSD, the Bonferroni approach, Tukey's pairwise comparisons, Chaffee's method, and Dunnett's method. All of these are called post hoc analysis because they're done after the ANOVA. And it's also important to realize that there isn't a perfect method. Each of these have their own strengths and weaknesses. Now that being said, it does tend to be better to plan out which of these you want to use and why, and which comparisons you want to make and why, before you run the analysis as opposed to after you run the analysis. So thinking this through, it's kind of weird because the terminology gets a bit confusing here. Post hoc means after the fact, a priori means before the fact, and pre-planned tests are better than post hoc tests or after the fact tests. But post hoc can refer to after you've run the analysis, but it can also refer to, after you've run the study, but it can also refer to after you've run the analysis. So we can actually have an a priori plan for post hoc analyses, which is saying that before we implemented the study, we created a plan for what we're going to do after a statistically significant ANOVA. So it kind of gets a little bit confusing. Just remember, a priori means before the fact, post hoc means after the fact. The post hoc tests mean after we ran the ANOVA, and they are good to design before we collect data for the study. So before we actually run the analysis, and actually if you follow our analysis plan that we outlined in the introduction, you'll note that you should have all of this identified before you implement the experiment, and that's what we mean by those pre-planned tests. Even the post hoc strategies that you're going to use, the comparisons that you're going to make, that should all be identified, or at least the method that you'll use to make such a decision should be determined before you actually see the data. Now, why is this better? Well, what ends up happening is if you get non-statistically significant results, people start to say, well, what if we compared blank and blank? Well, what if we compared this other thing and this other thing? Well, what if we compared this third thing and this third thing? And they really start hunting for these different statistically significant comparisons. And when you start doing that, it's called p-hacking, it's called data snooping, but it tends to be pretty bad statistical practice. So what we really want to do, again, is make sure that these tests are planned beforehand so that we can say, well, after I run the ANOVA, I want to compare all of the different groups to each other, and that's my plan. That's what I'm going to do. And so in that case, you can say post hoc after the ANOVA, that's what I'm going to do, but I can make this decision before I've ever done the research. So I make the a priori decision to run these specified post hoc analyses. All right, well, let's talk about each one in a little bit more depth. So Fisher's LSD, we've already referenced. It's certainly the most straightforward approach. It is very liberal, and when I say liberal, I don't mean like politically liberal. In statistics, liberal means it's more likely to make a type 1 error. So Fisher's LSD is the most likely to make a type 1 error of all these. Why? Well, it doesn't make any adjustments for the multiple comparisons problem. So as we demonstrated with the multiple comparisons problem, if I ran 4 of these tests, my probability of getting a type 1 error is much higher than just 0.05. So that means that we're more likely to make a type 1 error. And it's because we're not making any adjustment at all for this problem. This is usually not the best method. It's funny because our textbook does this a fair amount, and it's really not the go-to. There's a lot of better methods that are just as easy to implement, but frankly, it's just too liberal of a method. Now, there are cases where if the stakes are low in the research and you're really just trying to highlight anything that could potentially have a relationship, Fisher's LSD might be a valuable option. But if you're actually doing research on some preset factor levels and looking for those relationships as part of your study, then you really don't want to be too liberal. You want to be a little bit more balanced. Bonferroni. Now, this is a correction that you may have heard before. Bonferroni is a very easy and flexible approach. The idea and concept behind the Bonferroni approach can be used in ANOVA, it can be used in t-tests, it can be used in chi-squared, it can be used in regression, it can be used with a distribution you've never heard of before. It is really, really cool because it is so flexible. Now, what Bonferroni does is it adjusts our alpha level to keep that family-wise error rate if we do a whole bunch of comparisons. So pretty much it goes back to that equation that I showed you where we calculated, well, what would the family-wise error rate be if I ran 4 tests? And it kind of reverse engineers that to say, okay, well, if I want the family-wise error rate to be this number when I run all these tests, what does the alpha have to be to make that happen with the comparison of each of the tests? And it's actually a really straightforward calculation. The alpha has to be the family-wise error rate divided by k. So if I want, if I'm going to run 5 tests and I want my family-wise error to be 0.05, then the alpha I actually use in each of the tests is 0.05 divided by the number of tests I use, 5. So that would be 0.01. So what I'm going to do is I'm simply going to compare my p-value to this alpha of 0.01 instead of 0.05, and I do that for all 5 of my comparisons. And what this does is it makes sure that because I'm comparing to a much more conservative alpha, that the family-wise error rate is protected. Now, Bonferroni is fantastic, and actually it's so widely used because it is so easy to use, and it's so flexible and so applicable so widely. However, Bonferroni is kind of like trying to pick something out of your teeth with a chainsaw. It hacks very, very much away at the type 1 error rate, and it drastically reduces it, but sometimes it reduces it too much. So the actual type 1 error rate is like 0.001 when you wanted it to be 0.05. So you wanted it to be a reasonable number, and it just goes way too conservative, so way less likely to make a type 1 error rate. And it sounds good that it's less likely to make a type 1 error. You have to realize that being less likely to make a type 1 error comes at a cost. And when you're less likely to make a type 1 error, you're more likely to make a type 2 error. Or said another way, when you're less likely to make a type 1 error, you're more likely to miss a real effect. So something was really going on and you missed it, and that's the problem with approaches that are too conservative. Tukey's HSD. So this analysis is probably the best in our list for pairwise comparisons. It gives the exact family-wise error rate for comparing all pairs of treatment means. It is more conservative than the LSD approach, but again, the LSD approach didn't make any adjustment for the multiple comparisons problem, and Tukey's gives the exact value. It gives the exact level of a reduction that you should do for the multiple comparisons problem, as long as you're just looking at the pairs of treatment means. So this is a very, very good default if you're running the pairwise comparisons. Typically, if somebody just wants to compare group means after their analysis, again, I default to this. And it's really good for unplanned comparisons as long as you're just doing the pairwise comparison. So if you're just comparing all the different pairs of group means, this is good because it lets you compare all of them. You don't have to make an adjustment. Oh, I thought I was only going to run 2 tests, so I did Bonferroni divided by 2. But then we ended up running 40 tests, so now I have to divide my alpha level by 40 and go back and redo it all. You don't have to play with any of that. Tukey gives the exact family-wise error for comparing all possible pairs. And so again, if people just start wanting to compare pair 1 and 2 and 1 and 3 and 1 and 5, then I'll just give them Tukey's HSD because it accounts for all of the pairwise comparisons. So then they can compare whatever pairs they want because all of those comparisons are already accounted for in the family-wise error rate. And again, it's really useful when you don't want to plan, well, which pair I'm going to look at. I just want to look at all the pairs to be able to compare them all. Pretty handy. A fourth method we have is Chaffee's method. Of all of these, it's the most conservative. It's even more conservative than Bonferroni. That's not always true. Depends on how many different tests you're doing, but it does tend to be the most conservative that we have. And again, because of that, it is the most likely to miss something. So power is the probability that you didn't miss something. This has very low power, indicating that it's a relatively high probability that you miss something. And that's not a good thing necessarily. Now this controls for all possible comparisons, and actually by default you may think that's what Tukey did. Tukey controlled for all possible pairwise comparisons, where I compared a group 1 to group 2. Chaffee's accounts for all possible comparisons. So let's say somebody wanted to do a combination between group 1, group 3, and group 5 and compare to group 2 and group 4. And oh, that didn't work. So I want to do a combination of group 1, 2, and 3 and compare to group 4 and 5. So these are like the contrasts that I was talking about in an earlier slide. Chaffee's method accounts for all possible groupings of groups that you could compare, not just the pairwise comparisons where you compare one group to a single other group. So this accounts for all of that. So if you're doing a whole bunch of these post hoc contrasts where you're allowing, 2 groups to be compared to 2 other groups or something like that, this is probably the most appropriate method. So if you're just doing pairwise, I'd use Tukey's. If you're doing contrasts post hoc and you didn't pre-plan that, if you pre-planned it and you just planned a couple, you could use Bonferroni. But if you didn't plan it and you're just kind of hunting for stuff, then you use Chaffee's. And again, this is very, very, very conservative. If you're just using it for regular post hoc pairwise comparisons, you'd much rather use Tukey because it does account for the multiple comparisons problem, unlike the LSD. It's not overly conservative like Bonferroni and Chaffee's. But if you're doing the contrast, you really should be using Chaffee's method. All right, Dunnett's. So Dunnett's is a little more specific than the other tests that we've discussed, but when it's useful, it can be very useful. Dunnett's is for a very, very specific experimental design setup, and that is when I have a control group and a variety of treatments. And what I'm trying to study is not which treatment is the best, but which of the treatments work. That is, the only comparison I'm making is between each of the treatments in the control group. I'm not comparing the treatments to themselves because I don't care which treatment is best. I just want to see which of the treatments work. That is, which one is better than the control group. So when I'm comparing a number of treatments to a single control group, that's when we can use Dunnett's. And one of the benefits of Dunnett's in comparison to an alternate procedure like Tukey's or Bonferroni is that Dunnett's has a higher power. That is, we're more likely to find a difference that's actually there if I use Dunnett's test than Tukey's test. All right, so let's kind of summarize real quick. Bonferroni is really flexible but conservative. Tukey is a good default for the pairwise comparisons. Tukey is what I tend to use if I'm doing pairwise comparisons, and again, I tend to use pairwise comparisons after an ANOVA unless I have a really good reason for combining groups. Chaffee's is conservative, but it really protects against data snooping. That is, if we're trying to just come up with, I don't know, again, mean 1 plus mean 2 minus 1/2 of mean 3. And is that different than mean 4 and 5? If we're doing some kind of weird contrast stuff, then Chaffee's is really a great method because it protects against accidentally finding statistical significance when you really shouldn't have. And then Dunitz has used it with a control group. You'll note that one is missing, and that's the LSD, and that's because it doesn't actually account for anything regarding multiple comparisons. But again, there is a world in which we could use it, and that world is when it's pretty low stakes, and I'm really just trying to identify potential differences that could be there, and I'm going to end up following that up with another analysis anyway. So though we're not necessarily going to implement all these, we're not going to do them all in R. The names and strengths are really good to know, and it's really good to be able to identify that. And of course, if you're in a situation where, oh my gosh, well, I really need Dunitz test, well, hopefully you can recognize the name and then go Google, how do I do Dunitz test in R? So we'll definitely do Bonferroni and Tukey in R, because those are the most common ones and probably the most useful ones for the pairwise comparisons that we'll be doing in this class. But knowing the strengths and benefits of these 5 most common post hoc analysis methods with ANOVA is pretty important. All right, well, in the next video, we'll be going into power analysis. And what does that even mean? What is power analysis? And talking a little bit about how we can do it.